time. Okay, so previously, what we've talked about is network equals a change in kinetic energy. Well, there's other types of energy coming up, and if you look below, there's potential energy, a couple kinds. Now, we're not going to get into, thermal and solar and wind energy. Those are real things and real energy conversion, but AP Physics 1 really limits us to mechanical energy. So it's mechanics. And so kinetic and potential are your go-tos. And so just know that what we write isn't the whole story, but it's all you need to know for the AP1 exam. And so before we get into that, we need to distinguish between conservative forces and non-conservative forces. And so we haven't really got into categorizing our forces just yet. And it's going to make more sense once I do both sets of lists. So I'm going to make the list for each. We'll make a little table here, and then I'll use an example to describe, okay? So just hold tight if you are like, what? Conservative, and then we'll say non-conservative over here. Okay, so I'm just going to make some bulleted lists. And so the first designation to distinguish between conservative and non-conservative forces is how they depend on the path of the object. And so conservative forces, again, this may not make sense right now. I'll use an example once we get our list done. Conservative forces do not depend on the path, or in other words, they are path independent. Where non-conservative forces are path dependent. Right, dependent. The other designation relates to the energy that they provide. And again, energy's coming, but conservative forces have reversible changes in energy, where non-conservative forces have not reversible or irreversible, I don't know what's more correct English, change in energy. And the next bullet is one of those in most cases, under traditional cases, just FYI. And so conservative forces are typically considered internal to the system. And so previously, our examples, it's just been one object. Maybe there's been, two people pulling on one object, but we haven't really talked about systems. And so now we're going to get into a system approach, and AP is big on systems. Well, typically conservative forces would be internal to the system, but non-conservative forces are typically external to the system. And you may be sitting there, okay, I get one is yay, one is nay. I get the difference there, but what is it? And so let me give you some examples, and hopefully that helps with what is going on here. So some examples of conservative forces, Fg, are gravitational force. Does gravity care what path you take? No, okay, gravity is gravity, right? And then the other one is a new one. Don't worry, we'll talk about it today. It's elastic. And I know you're thinking, why not an E? That's electrical forces. So again, there's some of these forces that we just don't study. We don't study electricity anymore. But Fs is a spring force. That makes a little more sense, but it's still an elastic force, okay? And don't worry, that's coming. And so an example of non-conservative forces, Well, we've got applied force, friction, maybe tension, okay, dot, dot, dot. Anything that's not gravity, anything that's not a spring. So for this course, our conservative forces are just those two. And the hint is they relate to potential energy. Don't worry, that's coming. But they have a related potential energy, both gravitation and elastic. But we don't have a potential energy for friction or tension or applied, and so those are non-conservative. And so here's an example. If you rub your hands together, it warms up, right? It converts to thermal energy through friction, right? Can I take that thermal energy and say, okay, thermal energy, now move my hands? Can we put it back into mechanics? No, we can warm our cheeks, but we can't put it back into mechanical. And so that frictional thermal conversion is irreversible. Irreversible, okay? The path dependence in terms of gravity, not caring about our path, it doesn't matter if I drop an object or throw an object. Does that change the force of gravity on the object? Does it change the height that it's going to fall? No. Now we know that, projectile motion is going to be different, but in terms of the work that gravity's doing on the object, gravity doesn't care. It's just trying to bring it to the ground, right? And so path dependence, is it reversible with its change in energy? I'll show an example. If you lift a book, you can lower a book. Gravity doesn't care, okay? But air resistance would matter. Air resistance would be like frictional, okay? You kind of get the spirit of those? Spirit. Not 100%, but do you get the spirit of it? Okay. So what is this potential energy that we speak of? Sometimes, not so much anymore, but it used to be, students said, oh, that's the energy. You have the potential to do work. You have the potential to move. So it's the energy of something at rest. I don't know if you've ever heard that, but get that out of your brain. You do not have to be at rest to have potential energy. But what both of these potential energies have in common, it takes a system approach. And what do I mean by that? You have to have a reference point. That's what they have in common. You have to have a reference point. And so earlier we said gravity and elastic or spring forces were conservative. They have an associated potential energy. And so both of these are going to relate to that conservative piece. And so what is gravitational potential energy? Well, let's backtrack. We've already looked at gravity as doing work on an object. And so work done by gravity on an object, very frequently we said it's the force of gravity that's parallel to the distance traveled. Back table, are you all ready for new notes? Nathan? Nathan, are we ready for notes? Okay. If I can hear you all the way up here, that's a little distractible. So we've already studied this. Well, let's look at just lifting an object. Whether it's extreme case like a roller coaster or elevator, just lift a book, okay? And so maybe we started out at an initial location, which I'm going to label 0 meters. This is my reference point. And I'm going to raise that book to some height above, okay? Or I could say, 5 meters. And so that book has a particular mass. We're going to move it this distance. What forces are acting on it? Well, y'all know we've got gravity. And then there's some kind of lift force. And I'll keep it easy for us today. What if it's moving up at a constant speed? And so these two forces are equal and opposite, right? Newton's first law. So there's old stuff. Well, the work done by gravity, is it positive or negative or 0? Uh-oh, you just took a quiz on this. Uh-oh. Gravity pulls down on the book that's moving up. Gravity would be doing negative work. Applied or lift would be doing positive. So the work done by whatever lift force would be positive. And if you're moving at a constant speed, the net work would equal 0. Just to tie it back to the old, right? Well, now let's get into this idea of potential energy. So potential energy is something you have, you, the object, have, as long as you reference your lowest point. It might be the ground, it might be, the tabletop above the ground. That's kind of the beauty of this reference point. It doesn't always have to be the same place. And so let's change color here. Gravitational potential energy, AP says, is a U, capital U, G. Why a capital U? Well, capital P is already taken, and they don't seem to like the double, right? And so a lot, depending on what video you watch, what book you read, it is very common for potential energy to be PE, okay? And since we got a couple, now we got to use a little subscript. What kind of potential energy? Well, this one's going to be due to a gravitational field. So what is it? Well, mg delta y is your equation. Now I wrote it just below the work equation because guess what? It's equivalent. Notice mg is fg. True story? Fg equals mg. Delta y can be a distance traveled in the vertical direction, right? Change in vertical displacement. AKA, by the way, some people actually don't use delta y, AP does, but you'll even see me use mgh, height. There's a height change, right? You travel a particular height. Well, that delta y is really about a changing potential energy, true story. But notice it's the same math as doing work of gravity. Now, I just said same math. It's not identical. Let's take a look at you raising that book. When you raise that book, your vertical position, your height is increasing, right? So that's a positive. It's going from 0 to something. So when you raise it, you go from 0 potential energy at the bottom to a positive potential energy at the top. So what's your change? You have a change in potential energy that's positive. Final minus initial. Something minus 0. Does that make sense? Mathematically, Fg times D, mgh, you're going to get the same value. But notice the sign is different. Well, is it only different this one time or is it different all the time? Let's quickly lower the book. And so what if we start at a high point, some height, right? Not 0. And then we end at 0 meters. So now our book is going to travel downward. Well, gravity is acting downwards. We're supporting it. It may not be moving up, but we still have an upward force on the book if you just lower it. Normal force if you're in an elevator. And so now gravity is doing what kind of work? Positive. What kind of change in potential energy do we see? Negative. I go from something to nothing. Final minus initial, 0 minus something, is a negative. And so the difference between calculating work of gravity and a change in potential energy is just a sign change. The numbers are going to be the same. Does this kind of make sense? Do you see it? And so what this gives us is our second version of the work energy theorem. And so I'm going to slide over. So the work energy theorem, that's how it is on the AP formula chart. Our first version was net work equals a change in KE, change in kinetic. Our second version now has to do with gravity, and I'll tell you ahead of time, we'll see the same thing with elastic potential energy. And so this is what they have in common. The work done by conservative forces is equal to a negative change in potential energy. Now, I'm not going to put a G there because it's also going to be true for springs, but it's this sign difference. So there's your second version, not on the formula chart. A little bit more with potential, and then we'll pause for questions. So we've raised the book, we've lowered the book. By the way, you can still accelerate them. You can change kinetic as well. Think about the last time you rode a roller coaster. Did you change height over and over and over? Yeah, up, down, up, down, up, down, up, down, right? A lot, a little. Did you change speeds a lot? Yeah, and so you don't have to have constant speed in order to have this change in potential. It just simplifies it. Well, another thing with potential energy, let's take a look at units. And so units, mg, kilogram, times meter per second squared, times a height. We got another meter. What is this? Again, unit equivalence, you got to be ready to do this on the AP exam. And so kilogram times meter per second squared, it may not look like it, but think about mg. Mass times acceleration simplifies to what unit? A Newton. Mass times acceleration. And a Newton times a meter is a joule. Just like kinetic energy was a joule, potential energy, SI unit joules, okay? So it's still a joule. Okay, questions on potential energy. Gravitational, this is when you have a height change in a gravitational field. Got to have that reference point. If I did not designate 0 meters, would we know if the height, how the height's changing? No. And true story, you can make 0 meters the ceiling and raise and lower. It just flips things around. A little bit not the norm, but typically 0 meters is your lowest point. Okay. Talking about elastic, so springs, by the way, you can also have elastic bands like a bow and arrow, like a slingshot, like a ponytail, when you're talking about elastic potential energy. It's anything that has that compression, stretch, give, okay? The springiness of it. And so overall, elastic potential energy, I'm gonna go on and give you the equation, and then I'll explain with Hooke's law. So this one, wait for it. Hopefully it all ties together. And so now, elastic potential energy, still a U. Now we're going to say US. Same thing as saying PES. And you're like, why not an E? E is technically electrical, which we don't cover. So what's the equation? Well, it still has that force times distance reference, but when you stretch something, the force is not constant like gravity. It's more like an average force. And so it turns out to be 1/2 K. Ooh, I need to write a lowercase k. Be careful with your caseage. So this is a lowercase, and then delta x squared. So this is a derived equation. Hopefully either today or next class, I'll show you a graph and I'll show you how that equation is derived, but it's because the force is not constant. So 1/2 kx squared, it's a delta x technically. I don't know what AP does, if they say delta x or x, but I prefer delta x. Delta x stands for displacement. And it says you got to change. So remember earlier I said you have to have a reference point. Your reference point with springs and elastic bands is usually a displacement from equilibrium. And I'm not talking about Newton's first law equilibrium. Now it's a location for us. And what is a lowercase k? Well, I warned you because capital K is kinetic energy. Lowercase k is something called a spring constant. Or if it's a rubber band, it would be like an elastic constant. Some textbooks also call this maybe a force constant. Don't worry, we'll explain it. And then I'm going to change colors and put quotes on the word constant. This is one of these things that just nitpicks at me over the years. It's called a spring constant, bless you, but it's not always constant, bless you. And so to talk about this, everyone knows in a clicky pin, there's a spring, right? Did you know your cars have springs? It's in the suspension, the shocks. They wear out over time, right? And so the clicky pin today, what if I took that spring out and kind of played with it and I stretched it out and then, I put it away for 10 years. 10 years later, is it going to have the same level of springiness? No, it's stretched out. It's old, right? Things wear out, entropy, right? Over time. Rubber bands. I know I have thick hair, so the ponytails, the rubber bands I use, I didn't save them from 10 years ago, okay? They wear out over time. Your car, the shocks, the springs, got to get them replaced. And so it's only constant in the moment, in the present, okay? And it's not even constant from pin to car. Those springs look very different. A clicky pin spring, a thin piece of metal, right? Easy to move. Do we want a lot of springiness in our cars? You replace the shocks because you're bouncing all over the place. When you go over a speed bump, you don't want to be bouncing 30 seconds later, right? You want it to restore equilibrium quickly. And so you want a bigger, a stronger spring constant. Everyone get a feel for why I put constant in quotes? It's constant in the present tense, okay? Well, how do you figure out this spring constant? Well, for that, we need to slide over to Hooke's law. And so what is Hooke's law? This is on the formula chart. And so this elastic force or spring force is equal. Now I'm going to go on and put a negative and then K delta X. And again, that's a lowercase k. It's not kinetic energy. It's spring constant, spring factor. And so this negative sign, you'll notice on the formula chart, they put absolute values. So they say, oh, don't worry about the sign, at least when you do the math. But I'll be honest with you, they want you to know about relationships. This negative sign is not really for K. K's are always positive. It's for the relationship between the spring force on the object and the displacement. And to explain that, I'm going to draw a picture. And so, let's take a spring. So we'll stay horizontal. I don't want to change gravitational potential energy on top of elastic potential energy. So we'll just, no height change. And so think about this as 4 pictures. We're going to do 4 progressive pictures. And then I'm going to draw a dashed line over here. This is what I'm going to call the equilibrium location. So to get everything started, maybe my box is at equilibrium and we attach a nice spring to it. Okay. We're not moving. So I'm going to say my velocity is 0. Okay. We're just sitting there in our happy place, in our resting place, AKA the equilibrium. It's where the box wants to be if you leave it alone. Well, now let's do work on this object. Now, notice I said, let's do work. Let's compress the spring and move the box to the left of where it wants to be. So we did work and we just hold it in place for a second. Now, focus on the spring. The spring is pushing on the box what direction? The spring is trying to push the box towards equilibrium. It's trying to restore equilibrium, right? Get back to the happy place, box. And so the spring is pushing it to the right. Let's go standard sign convention. I'll call that a positive. But it's on the left side of equilibrium. And so being on the left side of equilibrium, it would have a negative change in displacement. Positive, negative, force displacement. That's why the negative is in the equation. You may not have to worry about it mathematically, but you do need to know that relationship. Does that make sense? Okay. And so we've done work on it. We've compressed the spring. It has elastic potential energy, right? Y'all know if I were to take a slingshot and go, compress something or stretch something, if I pointed at you, you know what's gonna happen, right? If I let go, don't let go. Because it has energy. We've done work to give it energy. Now let's let go. Now it's just the spring in the box. What's going to happen next? We let go. The spring is going to push the box. What direction? It's going to push it to the right. Would you agree that at some time in the future, the box is going to pass through equilibrium again, right? And so the spring, hey, it looks like it's in its happy place. But now it had all that potential energy. It's going to speed it up. And so now it has a velocity to the right. If you are at your happy place, equilibrium, does it have any displacement from equilibrium? What would delta x be when you pass through equilibrium? Displacement from equilibrium, at equilibrium, it would be 0. At this instantaneous moment, the spring is not pushing you, right? Objects in motion, they just want to continue in motion. And so when you pass through that equilibrium, the spring, for a very short amount of time, instantaneous, has no force on the box. Now it's moving. It doesn't stop at equilibrium. What's our next picture? Where's the box going next? See? It's going to keep going to the right. And yes, springs, they compress, but they also stretch. And so now let's show a stretched spring. Okay. It had all that velocity to the right. It's not going to stop until it slows down. And so now if I'm at max stretch, now my velocity returns to 0. Notice I'm on the right side of equilibrium. So I have what kind of displacement? If you're on the right side, you now have positive displacement. And what about the spring? What direction would that spring force be on the box? It would be in the negative direction because it's trying to pull it back towards equilibrium. So that spring force is always trying to pull the object towards equilibrium. Okay? Is this making sense? The progression? Don't worry, there's tons of simulations that show this. I'll try and remember to show you next time. Okay? But that's why the negative sign is in Hooke's law. Okay? So Hooke's law is how you basically get the spring constant. And so if you stretch it a little bit, that's a little force. If I stretch it a lot, that's a lot more force. Okay? And so this spring force is not a constant force. It's based on the displacement. So what if we were to solve this for spring constant? Well, it would be the negative ratio of force over displacement. And that's a lowercase k. I'm trying. And so what is the unit for our spring constant? So the unit would be a force Newton divided by a displacement meter. Hey, that kind of sounds familiar. Is a Newton per meter equal to a joule? No, so careful. Per is not the same thing as multiplying. So a Newton meter equals a joule, but a Newton per meter does not equal a joule. Everybody good there? Okay, so the unit for your spring constant is newtons per meter. And this kind of tells us a little bit more about springs. And so the bigger the K, that means the more force per meter it can support. Not every spring has to stretch a meter. It's just, is it able? What's its ratio? And so it means the bigger the K means the stronger the spring. Or elastic band. Okay, not all elastic bands are the same. Okay, think about a little rubber band that you might, tie your hair or tie some pencils together compared to a bungee cord. That's springy. I hope it has a bigger constant. I hope it can support more force if you're going to jump off a bridge, right? Don't try that at home. Okay. And so the bigger the K. So moral of the story, those car springs, they might be in the hundreds and thousands, triple, 4-digit spring constant. But our little clicky pin, maybe it's 3 newtons per meter. I've never tested a clicky pin spring, but it's not going to support a lot of force. And the other flip side, which one's easier to move? A clicky pin? Yeah. Okay, so that's a weak spring constant. I can move it real easily. I used to have a car spring, okay, it stayed at the high school, but I used to have one and you could stand on it and you couldn't even tell it moved, okay? Maybe it moved millimeters, but it was pretty strong, okay? It had a very high spring constant. Will you let him in? Okay, questions on Hooke's law with springs. Our spring, simulation that I have there, it's not moving, but our progression, okay? And then potential energy. So when do you have maximum potential energy? Well, spring constant is what it is for any given spring. It's when you have maximum displacement. And so if you compare that to the picture, at the ends, at full compression or full expansion, or stretch, that's when you have a lot of elastic potential energy. Watch this. What if you double the stretch? What would that do to your energy? If you double the stretch. Imagine I have a slingshot right now. You may not be scared if I just pull it back 5 centimeters, right? But what if I pull it back 10 centimeters? Doubling the stretch distance or compression does what to the energy? displacement squared. It would be 4 times the amount of energy, okay? 4 times the amount of energy. Okay, elastic spring, it's conservative, just like gravity. And so that work energy theorem is still that conservative variation. Well, what about non-conservative forces like, hold on. What about non-conservative forces like friction and applied? What kind of energy do they change? Well, it's actually, they can change both. You can apply a force to speed something up, right? Or friction slows an object down. You can have changes in potential all along the way. And so this next one is kind of big picture. Our last variation of the work energy theorem is about the non-conservative forces. And later on, I'll simplify these to WC, WNC, just to save a little bit of time. And so this equals a change in mechanical energy. What's mechanical energy? By the way, AP Physics 1, all we do is mechanics now. And so a lot of times AP will just say, oh, it's a change in E, because we only study mechanical, okay? But what is mechanical energy? Well, mechanical energy would be the changes in kinetic energy and the changes in potential. These are the only 2 energies we look at, okay? Everything else would be considered work. So thermal energy, we consider that work done by friction, okay? And so that's the one I want to use, last thing, to explain conservation of energy, which is just an extension of the work energy theorem. And so that third one, by the way, I'm going to highlight all these. I would know them. Okay? I would know them. The only one on the formula chart is the one regular W equals change in regular energy. It's generic on the AP formula chart. Okay? I would say the 2 most common ones would be the first and third. Those are the ones you're going to see us use the most often. But the second one there, I'll show you why we need it. Okay, conservation of energy. Let's take those theorems one step further. And so last part, we'll get to, system nitty-gritties next time. But remember, we dealt with network and we said, well, work of gravity plus work of applied plus work ... right? Normal, friction. Well, the spirit of what we've been doing today is to categorize it as conservative and non-conservative. And so what if we say net work is all the works done by conservative forces, gravity, spring, and then all the works of non-conservative forces. So we're kind of categorizing. So this is a true statement. Network, sum up all the works. Well, let's plug in those energies, see what happens. Network, we can plug in change in kinetic. Conservative work is equal to a negative change in potential. Now, I'm not using a subscript there because I'm collectively including gravity and springs. And then your change in non-conservative, the work done by non-conservative was a change in mechanical, which was kinetic and potential. Is this a true energy statement? I got 1 energy on the left, 3 energies on the right, but it's a good thing we include that negative. By the way, it's most commonly forgot. A lot of people forget that that's a negative piece. And if you include it, notice potential energy takes care of itself on the right. It zeroes out. And then all you're left with is change in kinetic, okay? And so energy is conserved as long as you take everybody into account. So this is like accounting, right? Make sure everybody's accounted for. Now, we don't typically write the conservation of energy this way, okay? Here's how we would write it. And it actually comes from that third variation. And so that work done by non-conservative forces equals a change in kinetic and a change in potential. Well, each of these deltas has final minus initial, right? So each of these is a KE final minus KE initial, and then plus a final gravitation, final potential minus initial potential. Well, it still isn't really a conservation statement. It's still true. What if we add both initials to the other side? Last statement, initial kinetic energy plus whatever potential energy you have initially. Now I'm going to actually, be a little more nitty gritty, plus or minus your non-conservative work, plus maybe it's applied. You're putting energy into the system. Maybe it's friction and it's taking energy from the system. So just a little reminder to consider the type of work. And whatever's left over will get divided into possibly final kinetic energy and final potential. Good on that? And so this is typically how you write it when you take a conservation approach, but it's the same thing as doing a work approach. Work energy theorem, it's still the same thing. Conservation just kind of looks a little different. Same math though. Energy can be converted from one form to another. If I drop an object from a maximum height, it starts out with potential. And when I drop it, it gets lower, lower, lower. I'm losing, scratch that, I'm converting potential energy into what other form of energy? It speeds up, right? So where's that potential energy going? It's going into kinetic, okay? So conservation of energy, we don't create, we don't destroy, we convert, okay? Now, if it's friction or air resistance, things warm up due to friction or air resistance, then we can't get it back, but it's accounted in the non-conservative work, okay? Questions for me? Got a little bit more to do next time with systems, and we've already started talking about systems, but it's just a closer look at the nitty-gritty details of how AP says, how do you define a system? All right, that's it for today. Make sure you plug laptops in. What else? I think that's it for today.